Next, we're going to look at the average value of a function. So we know how to compute the average of a set of numbers. We add those numbers together and we divide by the total number of numbers. So next, we're going to look at, for example, a function f of x like this. So here's y is equal to f of x. And we want to compute its average value over some interval a to b. So it makes sense that, well, maybe the average value is some height somewhere in between. So it's some height, something like this. So we'll call that one f bar. So f bar for the average value of f. So f bar is the average value of f. And then say over the interval from a to b. So on the interval from a to b, f bar is the average output. So how do we define the average output? So one picture is the following. So the average can be defined in the following way. So we have some function that goes up and it goes down and it goes up again and it does all sorts of weird things. And so if you think about this as the area under the curve being fluid but incompressible, so the area is not going to shrink or expand, it's always going to be the same area. So if I take a box of area here and I transform it and move it around to over here, it's the same area. So it's kind of like a fluid, but I can kind of slide it and move it and shape it the way I want. So the idea is, well, what happens if we were to shape this area? So I want to preserve area, but change the shape of this so that the function is constant. So in other words, I have some area above the average. I'm going to move that down here and kind of fill it into this hole. And I have some area up here, and I'm going to take it and put it down here and fill it into this hole. So basically, I'm going to replace my function like this, a function that varies, with a constant function that has the same area between a and b. And I'll define the height of that new function, or the value of that new function, to be the average value. So it kind of makes sense to be a reasonable thing that you would define that way. So let's see, how would we figure out what the height is? Well, we know the area, so the area under the curve is just the integral from a to b of f of x dx. Now we want that to equal the area under our new graph, and our new graph is just a constant. It just has the constant value f bar, so it's f bar times the total change in x, so times b minus a. So f bar, the average value, times b minus a should equal the area under the original graph. So f bar is therefore 1 divided by b minus a times the integral from a to b of f of x dx. So this is the definition for the average value of a function f of x over the interval from a to b. So this is the average value of f of x over the interval a to b. So in other words, we look at the total area under the curve and we divide it by the total width of that shape, and that basically gives us the average height. It makes a lot of sense to define average value that way. Now let's look at the relationship between the average value of a function and the average rate of change of a function. So the average value of a function was defined in the previous slide. So we also said that the average rate of change, so this is just an interesting observation here, of a function is f of b minus f of a divided by b minus a. So this formula goes way back to when we first started talking about calculus. And it just represents so if you have a function doing some stuff like this, it's just the average slope, if you will. Now, the rate of change itself, so later on we discovered that the rate of change, or the instantaneous rate of change, we'll say instantaneous rate of change, was just the function f prime of x. So it would make sense if it were true that if I average f prime of x, I would get the average rate of change of f. average rate of change of f. That would be something that would make sense, because if you think about the car velocity example, the derivative is your velocity. So it makes sense if you take your velocity function and find the average value, you should get the average rate of change of your distance. In other words, you should get the average velocity. We've previously used this for the formula for the average velocity. Where were you at 5 o'clock minus where were you at 3 o'clock divided by 5 over minus 3. If you traveled 140 miles between 3 o'clock and 5 o'clock, it's 140 divided by 2, 70 miles per hour. It would make sense that if I apply my formula for the average value of a function to the velocity function, that it also gave me 70 miles per hour. So let's see if it does. So let's look at the average value of the function f prime. So the average value of f prime, we'll call that f prime bar, well, according to, and this is of course on the interval from a to b, so according to the formula, it's 1 over b minus a, integral a to b, then I just integrate my function, which this time is f prime, so I integrate f prime of x dx. Well, if I apply the fundamental theorem of calculus, I have an antiderivative for f prime of x, it's just f of x. So this is the same as 1 over b minus a times f of b minus f of a, because little f of x is an antiderivative for little f prime of x. But this is the same as f of b minus f of a over b minus a. So it's kind of an interesting observation that if you apply the formula for the average value of a function to the derivative, what you're left with is the average rate of change. It makes sense. The derivative is the rate of change of the function. If you average that, you should get the average rate of change. So that definition for average value is consistent with the previous ones that we saw on average rate of change and our previous discussion of derivatives. So if we average the derivative, you just get the average rate of change. So it's an interesting corollary.